Hello, my name is Batoul, and today we'll be talking about our project, which is the Atmospheric Water Generator version 2.0. But before the version 2 came the version 1. And let me take you on a journey of how that worked. This was actually built by previous senior design students for their senior design project. The way it works is, at the top over here, we have two fans, and these fans, they suck in the air over here. Then the air will go into the copper fins, where it will condensate. The copper fins over here are connected to the cold part of the peltier, and then the hot part of the peltier is connected to aluminium fins. The aluminium fins have at the back, each one of them have the fan. The fan is used to cool them as well as to capture the air. And then when the water condensates, it will be captured over here. And then to drain it, we have holes in the system. There are four sets. As you can see over here. But to power these fans, we use a solar system over here. The excess energy at night is stored in the battery, and to be able to build this, we used additive manufacturing. However, the deficiency of the system is that the blowers or the fan, they use a lot of energy. And thus we came about using a solar chimney principle, which is ours, which makes our system over here, the version 2, fanless, and we don't need that much of energy.
Okay, hello. My name is Mohammad Kataw, and today my group and I will be presenting to you version 2 of the atmospheric water generator. First, I'll take you through the presentation outline. We'll discuss the problem formulation and the short technical background. We will then go into our proposed solution and the generated CAD model. We will present to you our theoretical analysis and the CFD simulations performed. Along with the results attained, we will end our presentation with the conclusion and our ongoing future works. Now, what is the problem? Climate change and water scarcity are two major worldwide problems. Climate change, unfortunately, has played its role and increased the average world temperature at a rate of 0.18 degrees Celsius per year since the year 1981. Water scarcity is not only due to climate change, but is also due to the increasing population and the increasing demand on fresh water supply. Unfortunately, water desalination plants are not a perfect solution, especially for landlocked regions that do not have access to unlimited seawater. Hence why we are working on this project in order to allow for the extraction of fresh water from the atmosphere. What is the value of our project? As I mentioned previously, our project aims to extract water from the atmosphere via condensation. We will be using the climate change effect in our favor, where climate change increases the temperatures and the relative humidity in the air, hence allowing us to extract more water from the atmosphere. Our methods are active methods that require energy in order to operate. The different methods will be discussed in the technical background. There do exist some non-technical and technical constraints. Being lightweight, using renewable energy, and portability are some technical constraints, whereas ease of use and budgeting constraints are the non-technical constraints. Passive and active methods are the two methods for this project. Passive water extraction is a natural phenomena that occurs when water condenses on the surface via radiative cooling. Radiative cooling is the effect where a body loses energy and loses heat and decreases in temperature, hence water condenses on the surface of the body. Using this method, we can produce a maximum of 0.8 liters per day per meter squared of surface area. Some applications of this method include fog collection and aluminum plate collection, as in the figures here. On the other hand, active water extraction methods do require energy input in order to accelerate the water extraction using the thermoelectric cooling elements that are Peltier elements. These elements help reduce the surface temperature lower than the air due temperature, hence accelerating the water extraction process. In the industry, the active water extraction process can extract up to 200,000 liters per day of water. Smaller scale models can be used and can extract 15 to 50 liters per day, which exceeds the human intake requirement of water.
This is Husam, and I'm going to explain to you our updated design of our proposed solution. So as we can see here, this is our SolidWorks model. The new updated design, it will also be made using additive manufacturing made out of ABS or PLA. Starting at the inlet, we can see the fins that are angled at an angle of 15 degrees upwards to ensure that there are no particles or anything dirty that enters the duct itself. And after that, it is connected through this converging section that leads the airflow to the cold side heat sink, where the condensation of the water happens and it gets drained. And after that, in the air diverter, this is the solar chimney principle, where the hot air is coming out and it passes through the hot side heat sink. And between the hot side heat sink and the cold side heat sink, there is the Peltier element. And yeah.
I'm Sherif, and I'll quickly explain the theoretical analysis. So we use a lot of different equations to find the different variables we need. Some of these equations were empirical and some were analytical. I'll discuss just a few of them. Here, for example, we have the equation for T, which is the temperature profile along the fin. We also have V, which is the amount of volume of water produced through condensation. And we also have QC and QL. These equations are to find the convective heat transfer coefficient and latent heat transfer coefficient, which will help us find the total heat transfer coefficient. So we took all these equations, put them in a MATLAB code, and the following results were obtained. First, we want to see the effect of relative humidity on the heat transfer coefficient. As you can see here, from any temperature, we can see that as the relative humidity increased, the heat transfer coefficient also increased. Another thing we wanted to test was the effect of the ambient temperature. Also, when you can see here, the heat transfer coefficient also increases when the ambient temperature increases. Now we'll see the effect of both of these variables on water generation, or how much water was generated. So here we can see the same effect as your relative humidity increases, volume of water generated increases as well, and when the ambient temperature increases, volume of water increases as well. Now this is just the temperature profile we plotted. As you can see here, when we increase, first we'll discuss the effect of the ambient temperature. When the ambient temperature increases, the rate at which the temperature changes to the ambient temperature also increases. And when the humidity increases, the same effect can be seen. The rate at which the temperature along the fin reaches the ambient temperature also increases.
Hello, my name is Batoul, and today I'll be guiding you through the CFD simulations. So we performed some CFD simulations and answers for our the 3D model of our design, mostly to be able to obtain the velocity contours, the temperature, as well as to check if there is any water that's being generated. For the first part, we did a velocity contour for our design. We simulated the flow of 1 meter per second with a 15-degree angle for the wind catcher at the inlet. But as you can see over here, the velocity increases to more than double throughout the duct, which is something that we require, because the higher the velocity, the greater is the coefficient, the convection heat transfer. And over here we can see that the maximum velocity occurs over here, because there is a change in the geometry. Over here there are the extended copper tubes in the heat sink. Moving on, we also did temperature volume rendering. We can see we simulated the flow for 45 degree, which is about 318 Kelvin. The reason for the entirety of the color being the same is because the range falls within the same contour. However, at near the hot part of the Peltier, we can see that there is a high velocity, there is high temperature. We also use the multi-phase model, mostly to be able to see if there is any change in the mass transfer rate or mass fraction, to see if there is any water being generated. Over here we can see that the mass transfer rate decreases and goes negative around the cold part, the cold fins, which is where we actually anticipated that there is water being generated. Then we also did mass fraction of water. We simulated it at 80% humidity, which is equivalent to a mass fraction of 0.05. But at the end it ends up being at around 0.022, which indicates that there is some water being generated. Calculating that amount, we get from ANSYS about 0.025 liters per 30 minutes. However, comparing that with the theoretical values that we did in MATLAB, we get around 90.5% difference error, and that error is contributed due to two reasons. One is the fact that we did a lot of assumptions in both the numeric in ANSYS and the theory, And the second reason is that in ANSYS we did not use a user-defined function for the condensation. But this error only tells us that we need to build a prototype and carry out some experimental result to cross-check it with our theoretical values.
So in conclusion, moving on to by looking at the theoretical results, we can see that the wet temperature along the fin increased due to increases in surrounding temperature and relative humidity, and this is because the increase in surrounding temperature and the relative humidity increases the heat transfer to the fin. Also, because the surrounding temperature and the relative humidity are directly proportional to the mass flux, the volume of generated water increases as the variable is increased. From the simulation, we saw that the inlet velocity doubles around the cold side of heat sink thanks to the improved design of the duct, and water is being produced in the duct around the sink and it's getting drained, which is our main aim of the project. For the ongoing and future works, the most important thing, as we said before, is to manufacture the working prototype to obtain the experimental results. And by the end of this presentation, we would like to acknowledge our course instructor and supervisors, Dr. Mason, and our lab engineers in the American University in Dubai.